Thank you for attending the IES 2022 Annual PI Meeting. My name is Dory LaForette, and it has been my pleasure to serve as co-chair along with Dr. Brian Boyd for the meeting. At this time, I'm happy to introduce Dr. David Francis, who will be giving our closing plenary. Dr. Francis is the Hugh Roy and Lily Kranz Cullen Distinguished Chair of Quantitative Methods in the Department of Psychology at the University of Houston, where he serves as director of the Texas Institute for Measurement, Evaluation, and Statistics. He currently collaborates on multiple contracts and grants funded by NICHD, NINDS, the Office of Naval Research, IES, and the Office of Elementary and Secondary Education. Having directed a previously funded IES National Research and Development Center from 2005 to 2012, Dr. Francis currently serves as director of the IES R&D Center for the Success of English Learners. Dr. Francis is a frequent advisor to the Department of Education on statistical and psychometric issues, assessment and accountability, learning disabilities, and English language learners. He has served on numerous governmental advisory panels, including the National Board of Education Science for IES. A recipient of many honors, in 2021, he received the Hedges Lecture Award from the Society for Research in Educational Effectiveness. In keeping with the meeting theme of diversity, equity, and inclusion, Dr. Francis' presentation is entitled Planning for Diversity in Educational Research, Design, Measurement, and Analysis to Advance Equity and Inclusion. This talk acknowledges that while we strive to develop knowledge in education science that is generalizable and replicable, most research barely scratches the surface of accounting for the multiple levels of diversity in the education system. While these limitations partly arise out of constraints on resources, too often they arise out of researchers' concerns over proper design, measurement, and analysis to accommodate diversity in study samples. This final session will examine the topic of diversity in education research in an effort to empower researchers to take the broadest possible view in individual studies, while also taking the long view on their research and considering the value of building diversity over time in one's research. Please join me in welcoming Dr. David Francis.
Thank you, Dory, for your gracious introduction and for the invitation to present at this year's IES PI conference. I also wish to thank our attendees and speakers at the conference. Hope that everyone's 2022 is off to a great start and appreciate that people have taken time out of their schedule to attend our session. Diversity is ubiquitous at all levels of the education system, from students to teachers to parents and administrators, schools, districts, and states. Most research can barely scratch the surface at any one level, and yet we strive to develop knowledge in education science that is generalizable and replicable. Limitations understandably arise out of constraints on resources, but they can also arise when researchers fail to plan for diversity through proper design, measurement, and analysis. This final plenary session of the 2022 annual PI meeting will examine the topic of diversity in education research from my perspective as a psychologist who's been immersed in education research for over 3 decades. My hope is to inspire and empower researchers to take the broadest possible view that makes sense in individual studies. While I also hope to inspire you to take the long view in your research and consider the value of building diversity over time in one's research, I found it impossible to serve both masters in one talk. I will tell you that it is possible to build understanding and to increase the sensitivity of your studies to specific aspects of diversity within your areas of interest over time. Perhaps we can touch on this aspect of research in the Q&A to the extent that it is not adequately addressed through the talk itself. My research has been supported over the years by IES and the National Institutes of Health, but the opinions expressed in this presentation are my own and do not reflect the opinions or official position of IES, the U.S. Department of Education, the National Institutes of Health, or the federal government. Although I've collaborated throughout my career with amazing colleagues, please understand that they are also not responsible for the content of the presentation. Education is unique, if for no other reason that we all have our own experience with learning, and most of us have some experience trying to learn from inside an education system. For better and for worse, these experiences shape our thinking, attitudes, beliefs, and feelings about education. As education researchers, we are aware of and work to overcome the operation of these forces, but we're not immune to them. Like all of you, important aspects of my background have shaped my perspectives on education, which I see unequivocally as a force for good in the U.S., albeit an imperfect one. My grandfather was born in Venezuela, but I'm not Hispanic. My father would have been considered a language minority student because his parents spoke Arabic in the home. He would have also been considered an initially fluent English proficient language minority student, as he spoke only English his entire life. Of course, he was born in 1928 and went to school at a time that predated such ideas by decades. My father was the fourth oldest male child in his family, but the first to attend school past grade 8, despite his mother's asking him to quit school to help support the family. Rather, he worked after school and became the first in his family to graduate high school, a decision that significantly shaped the course of his life and the lives of his children. Although I have not been everywhere, I have traveled extensively throughout the world, having visited all 7 continents, and have lived in a non-English speaking country for 6 weeks to 6 months on 3 separate occasions, twice in Germany, and I hope to do so to have that opportunity again. I was born in Detroit, but I've lived in Houston since 1979, and throughout that time, Houston has been one of the most diverse cities in the United States, lacking an ethnic majority for at least the last 21 years, at least since the 1990 census. As of 2015, if the Houston area were its own country, it would actually rank among the top 5 countries in the world for refugee resettlement, according to an article by Andrew Craigie. And it's not just where I live that's diverse. The University of Houston, where I've been on the faculty since 1985, is said to be the second most ethnically diverse campus in the country. The demographics of the University of Houston and of the public schools in Houston reflect the diversity of the city. The University of Houston is a Tier 1 research university that is also a minority-serving institution. It was ranked number 7 nationally among the top U.S. colleges and universities that pay off, which compares earnings to the cost of attendance. The University of Houston is listed among the top 20 schools nationally for social mobility and is a top producer of Fulbright Scholars National, according to the Chronicle of Higher Education. And it's ranked in the top 10 for serving Hispanic students in 4 disciplines. Roughly 40% of the University of Houston students have received a Pell Grant, and 43.8% of incoming students are actually first-generation college students. The Houston Independent School District is among the country's most diverse school districts. Over 100 languages are spoken by students in the district, and roughly 30% of the students are English learners. Of the district's 280 schools, 47 are dual language schools, including dual language programs in Spanish and English in both elementary and middle school. And the HISD also offers dual language programs in Arabic, Mandarin Chinese, and in French in elementary school. The Houston Independent School District is the largest of 54 districts in the greater Houston metropolitan area, the largest district in the state, and the 7th largest district in the country, with approximately 200,000 students in any given year. The quote above is attributed to Marvin Zuckerman in his written commentary on an article by Robert Plomin in Brain and Behavior Sciences in 1987 titled, "Why Are Children in the Same Family So Different?" I always understood the comment to be a call out to the role of temperament, and as a psychologist and the father of 2 adult daughters, that made perfect sense to me. In fact, the article by Plomin is about the role of non-shared environment and how the role of non-shared environment has come to be understood in the field of behavioral genetics as an important source of individual differences. I'm not going to try to adjudicate the roles of genes and environment or even the distinction between shared and unshared environment, but I do want to talk about individual differences. When we think about diversity, often the only thing that comes to mind is differences between groups that we identify along racial, cultural, ethnic, or gender boundaries. Perhaps what should come to mind are the substantial differences between people who are similar to one another on these easily identifiable demographic features. What made my father different that he valued education in a way that his parents and older siblings did not? When I asked him about it, he did not identify a specific person or influence in his life as the source of his insight. What the field of behavior genetics has made clear, and which no one disputes, is that, quote, children growing up in the same family are very different, end quote, from one another, according to Pullman. In education, the conversation about diversity will be strengthened when we move beyond group mean differences and focus instead on within-group heterogeneity, individual differences, and understanding students as individuals. I can't accomplish that today, but I hope to plant that seed and encourage the design and analysis of education studies that allow us to go beyond group mean differences and offer a better accounting of the factors influencing individual students and the ways in which those factors contribute heterogeneously to student outcomes. I'm going to approach the topic of diversity today from the standpoint of thinking about and studying English learners, a group of students who are demonstrably among the most diverse in our schools. These students have educational experiences that differ from their non-EL peers in ways that are difficult to fathom. Interest in this group of students from educators, policymakers, and researchers has increased significantly in the last 20 years. But despite significant improvements in our understanding, much work remains to be done. My goal is to broach the topic of diversity by way of an exploration into the language achievement connection for students who are English learners. Just by way of background, it's important to understand the distinctions that we make between students. For people who work in this particular area, these terms are going to be familiar. But insofar as many people do not work in this area, I thought it might be important to establish some common understanding about English learners as a group. In the United States, English is the societal language. An agreed upon terminology distinguishes those students exposed in the home to a language other than the language of the society from those who are not. This terminology further distinguishes those students who are not yet proficient in the language of the society from those students who are proficient. A language minority student may be fluent English proficient at school entry, whereas an English language learner is not, although it is expected that the student will become proficient in English via instruction, although, as we all know, the time to achieve proficiency varies greatly across students. This population of students is heterogeneous in many respects. They come from a diversity of linguistic backgrounds, at least 300 in the United States. They come from all socioeconomic classes, although they are disproportionately represented among lower socioeconomic status groups. They vary in terms of their experience in U.S. schools, with most entering U.S. schools in kindergarten. Nevertheless, many students enter U.S. schools in later years, including up through high school. Moreover, students who have not received all of their education in U.S. schools cannot be assumed to have had formal schooling outside the U.S., nor can they be assumed to have had uninterrupted schooling, whether inside or outside the U.S. Insofar as a disability is, by definition, a learning disorder not resulting from a lack of opportunity to learn, from a student's social class, or exposure to ineffective teaching, heterogeneity with respect to these other factors also complicates the identification of disabilities among language minority students. The presence of disabilities can affect students' development of proficiency in English, as well as their first language, and their acquisition of other academic or cognitive skills, depending on the nature of the disability. The identification and treatment of disabilities among English learners is an important and complex topic that reflects another dimension of diversity within the population. Unfortunately, we will not be able to address this topic further within today's talk. The slide shows a map of the U.S. that's color-coded for the percentage of students identified as English language learners. The data come from the IES Condition on Education and are the most recent data available. The map shows clearly that English learners comprise a substantial portion of the student population virtually everywhere in the U.S. Less apparent is how much the EL population has grown over the last 2 decades. The percentage of public school students in the U.S. who were English language learners was higher in the fall of 2017. It was actually 10.1% of the student body, or 5 million students, than in the fall of 2000, when it was 8.1% of students, or 3.8 million. In the fall of 2017, the percentage of public school students who were ELs ranged from 0.8% in West Virginia to 19.2% in California. The percentage of English learners exceeded 10% in 10 states and was below 3% in only 5 states, 3 fewer than in 2016. It is also important to note that statistics presented on this map fully ignore those students who began school as English learners but became proficient in English and have since been reclassified as fluent English proficient. For example, in Texas and California, if students who were ever English learners were counted in this map, they would comprise upwards of 30% of the student body in those states. Unlike most children whose first language is the language of the society, students who are English learners may experience one or more of a variety of instructional programs that differ significantly in their approach to language development and content area instruction. It's not necessary for us to get into a lot of detail on the variety of instructional programs for English learners. In fact, there are really only 2 points that I wish to make here. The first is that program labels are descriptive. There is heterogeneity within programs of the same label, and this heterogeneity affects students' development. The second point is that although the bilingual/native language programs differ in their objectives, these programs tend to be most different from one another in the later elementary grades, specifically from grade 3 and beyond, as compared to the early grades, kindergarten through grade 2. The difference in the later grades arises because some program models have as their goal the development of proficiency in both languages, whereas transitional programs rely on the student's first language primarily as a bridge to build proficiency in the societal language. As we move beyond the elementary grades, most students are in English-only instruction, although some dual language programs exist in middle school. And the question becomes whether English learners have access to grade-level content instruction and are taking courses with their grade-level peers who are proficient speakers of English. For students who are new to U.S. schools in later grades, despite there being, say, in an advanced grade in middle school or high school, some districts provide specialized programs and schools to assist students with this transition to U.S. schools. When we think about English learners as a subgroup of students, people invariably contrast the academic performance of English learners to their non-English learner peers. Of course, such comparisons suffer from a series of fundamental flaws. These comparisons are flawed because they ignore both the dynamic nature of the classification of a student as an English learner, and they ignore the heterogeneity within the English learner subgroup on the defining attribute, namely English proficiency. The English learner category is unlike other student subgroup categories because membership in the category is typically temporary and based on an attribute of student cognition that is developmental in nature, it is the focus of schooling, and it is causally implicated in student achievement. We've made attempts to address this issue by allowing students to, quote, count as English learners for a specified number of years after they attain proficiency in English, but the fact remains that the majority of students who begin school as English learners become proficient in English and are no longer counted in the English learner category as they continue to develop skills and more advanced proficiency in English. These characteristics of the EL category have led some researchers, specifically Bill Saunders and his colleague Marcelletti, to characterize the gap in EL performance as the gap that cannot go away. When we think about English learners, we think about language ability and language proficiency. And language ability is a determinant of academic achievement. That language ability is a determinant of academic achievement is true for reading language arts, it's true for mathematics, it's true for science and social studies and all other academic domains. But language ability is distinct from an individual's proficiency in a specific language. By highlighting the importance of language in learning and achievement, I don't mean to imply that all knowledge is verbal in nature. While there is such a thing as procedural knowledge, knowledge of how to do things, Much of what is disciplinary knowledge is not focused on how, but on what and why. And much of the how in disciplinary knowledge is because of why. We communicate much of what we know, both orally and in writing, through language. Even when we communicate through graphs and figures, we often use language to characterize what is known or learned from the figure or the graph. We'll experience that today as we look at data. It may seem extreme to say that world knowledge is synonymous with word knowledge in academic domains, but when we attempt to measure background knowledge separately from vocabulary, we find the correlation to be very near unity. This slide shows some data from the Reading for Understanding network studies where we attempted to actually tease apart background knowledge and vocabulary. These correlations span grades 7 through 12 and are based on samples of both good and poor readers, approximately 200 students per grade. They show that when we use multiple measures of these abilities, knowledge of the world, knowledge of words, and the ability to understand what one reads are essentially indistinguishable from one another. We're not the only group in the Reading for Understanding network that has found such high relationships across these three constructs when we remove the effects of measurement error. The Florida State group, led by Chris Lonigan, has similar findings for children in grades 1 through 7. This chart shows the percentage of variance in English language arts and math achievement scores for English learner students that resides at the student, the school, and the district level for English learners in grades 4 through 8 for a single school year for an entire state. Although these data are getting a little long in the tooth, they serve to illustrate the significant variation that resides at all three levels, with students accounting for 69 to 72% of the variance in English language arts and 57 to 68% of the variance in mathematics, with somewhat less variance at the student level in math in grades 7 and 8. Variance is roughly evenly distributed at the school and district levels in English language arts, but appears greater at the district level for math, ranging from about 17% to 29% at the district level and from 10% to 15% at the school level. In contrast to English language arts, where the percentage ranges from 11% to 15% at the school level and from 15% to 17% at the district level. More recently, Faley and Reardon 2018 have looked at district-level interclass correlations for English language arts and mathematics from 2009 to 2015 across the entire country. Their estimates are not restricted to the achievement performance of English learner students, as the charts here are. The charts on this slide are just for English learners. Faley and Reardon conclude that their analysis has confirmed prior work which showed that between district variation is larger in mathematics than in English language arts, and that between district variance grows over grades, a finding that is consistent with the figure above. So even though the data that I'm showing you are old, they actually are consistent with more recent data, I would say. I would also add that the present data, that is the data that I'm showing on this particular slide, are from one of the states that Faley and Reardon reported to have larger district level interclass correlations. In their entire country sample, that level was, the ICCs range from 0.15 to greater than 0.175. So again, those are consistent with what we're showing here. If we take into consideration the level of English proficiency of individual students, much of the variance in achievement at the school and district level is reduced. The table on the present slide shows the reduction in variance at the school and district level by including students' language proficiency classification, that is, whether they're in levels 1 through 4 of language proficiency. We can improve on these statistics, that is the amount of variance reduced at the school, student, and district level, if we actually measure students' actual performance by taking their scale score performance into account. But the point is, even by taking into account the level of their performance, we account for substantial variability at the school and district level. Thus, at least part of the differences in the achievement of English learners across schools and districts is due to differences in the distribution of English learners' language proficiency across schools and districts. Generally, this table shows that differences in student proficiency account for more of the variance at the district and school level in English language arts than in mathematics. Also, the proportion of variance accounted for at the school level in English language arts is somewhat greater in grades 7 and 8 compared to earlier grades. Whether these differences are due to programming, that is, to programming differences that lead to more protracted development of English proficiency for some schools and districts compared to others, differences in approaches to content area instruction, or differences in school composition with respect to beginning levels of English learners versus English learners with more advanced English proficiency, can't be determined from the data that we have available to analyze. But it's important to point out that only some of these factors are under the control of schools and districts. Others are not, such as the influx of students at different levels of English proficiency from one year to the next. One of the dimensions along which English learners differ from one another is their time in U.S. schools. These figures show the relationship of years in the U.S. to achievement as well as English language proficiency. The scale for English language arts and mathematics achievement is slightly different than for the English language proficiency assessment. Specifically, the English language proficiency scale ranges from 300 to 400 in each grade, whereas the English language arts and mathematics scales range from 200 to 280 in each grade. Across the horizontal axis, we have years in the US, and the vertical axis displays the achievement in English language proficiency scores. The red and gray, orange and gray lines are for the achievement tests, and the blue line is for English language proficiency. The English language arts and math assessments are scaled such that students must achieve a score of 240 to be considered proficient. However, a score of 220 or above is considered the minimum score needed for graduation from high school. Although the higher score of 240 is used for determination of adequate yearly progress, and the lower score of 220 carries a formal designation of needing improvement, the lower score can be considered a minimum passing standard insofar as it is the minimum score with which students can meet the requirements for high school graduation. The minimum standard of 220 may also be considered a level of performance on the English language arts and math tests where it is reasonable to expect that students are able to perform regular classroom work in English. If we look at these figures, they show that English language proficiency, English language arts, and math performance increase fairly steadily as the number of years in the U.S. increases. This relationship holds in all grades 4 through 8, although the relationship is somewhat stronger in the earlier grades and is considerably stronger for English language proficiency. For example, in grade 4, English language proficiency performance increases from 347 to 382 from 1 to 5 years in the US, whereas English language arts increases from 223 to 226, and math increases from 220 to 226. While the greater increase for English language proficiency is due in part to the greater variance in English language proficiency, that is, that scale difference, the standard deviation for English language proficiency is 26.71, and the standard deviation for English language arts is 12.19, and for mathematics, 14.3. This difference does not fully account for the differential effect of years in the US across the three domains. If we measure the differences in standard deviation units, the difference in English language proficiency for students with 1 versus 5 years of experience in US schools is about 1.29 standard deviation units as compared to 0.25 standard deviation units for English language arts and 0.42 standard deviation units for mathematics. The same general pattern applies in all grades, although the gains in English language arts and math are less in grades 7 and 8 and are negligible for math in grade 8. In addition to the differential effects of years in the US across the three domains, It is readily apparent that the largest differences due to years in the US occur from 1 to 4 years, with somewhat smaller differences between 3 and 4 years than between 1 and 2 years or between 2 and 3 years. These conclusions are supported both for the mean performance results graphed on the current slide, as well as for the percentage of students scoring at or above the minimum passing standard for each measure. That is, whether we focus on the average performance or the percentage of students meeting the minimum passing standard, it appears that effects of years in the US is stronger for the English language proficiency assessment than for English language arts or mathematics, and that differences are largest up through 3 or 4 years, depending somewhat on the outcome and grade. The weak effects of years in the US are perhaps more apparent if we examine the entire distribution for English language arts and mathematics, which we'll do on the next slide. So the impact of years in the US is displayed graphically on this slide, which provides a histogram of English language arts and math performance by grade and years in the US. The figure is divided into 2 graphs. The left-hand graph displays information on English language arts performance, whereas the right-hand graph displays information on math performance. So each thing is a sort of scatter plot matrix, and each scatter plot matrix is arranged in the same way. So each graph is arranged as a table, with the columns of the table representing the separate grades and the rows of the table representing the different values of years in the US. The table is ordered such that the leftmost column corresponds to grade 4 and the rightmost column to grade 8. Similarly, the bottom row corresponds to 1 year in US schools, and the top row corresponds to 5 or more years in the US. Arranged in this way, one can see the effects of increased years in the US within a given grade by scanning the column for that grade from the bottom row to the top row of a given graph. So for example, on the left-hand side for English language arts, 4th grade, going from 1 year in the US up to 5 years in the US. One can also see the effects of grade within a given number of years in the US by scanning along the row for a given value of years in the US. The figure shows the general trend towards increasing average performance between 1 and 4 years in the US and highlights the marked variability in performance across students in the same grade and with the same number of years in the US. At virtually every level of years in the US, the entire range of scores on the English language arts and mathematics assessments is observed, with a higher percentage of the distribution falling above the minimum passing standard of 220 as the number of years in the US increases through 3 or 4 years. This observation holds for both English language arts and mathematics and for each grade 4 through 8. The passing standard, just for reference, is the second hash mark from the left-hand edge of each figure. It must be kept in mind that these differences are being measured cross-sectionally. That is, these differences are not based on changes in performance for particular students. Rather, they reflect differences in the performance of different cohorts of students who entered the US at specified point in time in the past and who are in the same grade in the present year. Consequently, one must be cautious in attempting to interpret these differences as the change that is expected for individual students as they spend more time in the US. There are several factors that make such interpretations difficult. First, the observed differences reflect cohort differences in addition to any possible effects of additional time in US schools. Secondly, as students spend an additional year in school, it is also expected that they will change grades. For example, advance from grade 4 to grade 5 or from grade 5 to grade 6. Thus, to see the effects of advancing a grade and adding a year in US public schools, one would compare means from different grades that also differed according to years in the US. For example, to see the effect of an additional year in public schools for grade 4 students with 1 year in US schools, one would compare the mean for grade 4 students with 1 year to the mean for grade 5 students with 2 years. You can simulate this comparison by moving sort of diagonally across the figure as you go from one grade to the next, but also advancing in 1 year of schooling. Of course, this comparison is also potentially biased as a measure of longitudinal change and is not a substitute for actual longitudinal measurement to accurately evaluate student level change associated with increased time in U.S. schools. Nevertheless, it gives another perspective on the change that might be expected due to additional time in U.S. schools. So as we saw when we examined the variance at the student, school, and district level, there's a strong relationship between performance on the English language proficiency assessment and both the English language arts and mathematics assessments. This relationship holds for each grade 4 through 8 and is especially strong between the English language proficiency assessment and the English language arts assessment. For English language arts, students are almost twice as likely to achieve the minimum passing standard if they have reached the transition level, which is level 4, on the English language proficiency assessment as compared to the intermediate level. If we examine the relationship between English language proficiency and achievement graphically, it's also apparent for both English language arts and math that the variability in performance increases as English language proficiency increases. The figures presented here are designed to show the relationship between the English language proficiency scaled score and English language arts in the left-hand set of graphs, or math in the right-hand. So it's organized similar to the previous slide, with a scatter plot matrix for English language arts on the left and a scatter plot matrix for mathematics on the right. And again, in both graphs, each plotted symbol reflects the performance of an individual student and shows where that student scored on the English language proficiency and English language arts assessments or the English language proficiency and mathematics assessment. Both figures are organized like the preceding figure to show the effect of changes due to years in the US. So again, the rows of each matrix reflect the number of years, and the grade reflects the column, is reflected in the column. What is shown in each cell of the scatter plot matrices is the relationship between English language proficiency performance graphed on the horizontal axis and performance on the content assessment graphed in the vertical axis. In the margins of the figures, I've placed some lines that show the passing standard on the achievement test. So these arrows on the vertical axis show the performance standard, passing standard on the achievement test, and for the English language proficiency assessment here on the horizontal axis. The large circles in each figure give you a rough idea of the individual data points that fall above both passing standards. So the students who are passing both the language proficiency test and the achievement test standard. One thing that stands out when you look at these figures is the increase in variability in achievement at higher scores on the language proficiency assessment compared to lower scores. This increase in variability at higher levels of performance on the English language proficiency assessment is reflected in the increased spread in the cluster of points within any given cell of the graph as one scans from left to right within the cell. The relationship does not appear markedly different within a grade for students with different numbers of years in the US. That is, if you look across the rows of any given column, you don't see a big difference. And the increase in variability in English language arts and maths associated with increased proficiency in English language proficiency could represent various factors that might be operating either alone or in combination. For example, it's possible that students need to reach a particular level of performance on the English language proficiency assessment before English language proficiency performance begins to affect performance on the English language arts and mathematics assessments. Such a threshold phenomenon could occur if the factors that drive performance on the language proficiency assessment at the lower end of the scale differ from those that drive performance at the upper levels of the scale. and that is only those factors that drive performance at the upper ends of the scale that are related to English language arts and mathematics performance. Alternatively, such a threshold effect could also obtain if the floor of the English language arts and math assessments don't reach low enough. Of course, the purpose of the English language arts and math assessments is to cover the respective domain in each grade, not to cover the full range of linguistic competence that's observed within the English learner population within any given grade. Similarly, this threshold effect and consequent increase in variability at the upper end of the English language proficiency scale could obtain if the English language proficiency scale has insufficient ceiling. That is, if the range of the English language proficiency assessment were extended, the overall relationship between English language proficiency and English language arts or mathematics achievement would be linear and wouldn't show increased variability at the upper end of the English language proficiency scale. One possible interpretation of the pattern of relations is that of differential validity of the English language arts and mathematics assessment for students at different levels of performance on the English language proficiency assessment, or if not differential validity, at least differential utility of the English language arts and mathematics assessments. Insofar as performance on the English language arts and math assessments do not vary much at low levels of proficiency on the English language proficiency assessment, one might argue that the former assessments are not providing useful information until students reach a point on the ELP assessment, that is the language proficiency assessment, where subsequent changes in performance will be associated with changes in English language arts or mathematics performance. However, this interpretation is strictly dependent on the current state of affairs with regards to instruction. In other words, the current relationships among these tests reflect the specific construction of these assessments and the way that instruction was approached with regards to English learners at the time that these data were collected. If the language standards of the language proficiency test or the content assessments were closely aligned, if the language proficiency assessment emphasized academic language development at the low end of the scale, where teachers engage students in content area knowledge development regardless of their level of language proficiency, these relationships might reasonably be expected to change. One thing that's reasonably clear from the figures, regardless of the reason or reasons for the observed increase in variability in English language arts and math performance at the upper end of the language proficiency scale, this phenomenon and the general relationship of the English language proficiency and content assessments are both consistent across grades and content areas, and neither appears to vary considerably as a function of years in the US. So we don't see something different as we move from row to row within any given column. So the one question that was raised based on the previous set of graphs is the question of differential validity or possible validity challenges for the achievement assessments. And there are several different ways that we might take to interrogate the question of differential validity of the content area achievement tests. I would like to show you an approach that is person-centric and combines item response modeling with latent class or mixture models. This item mixture model will combine item response and latent class models by modeling item level data and hypothesizing the existence of two latent classes of English learners, one for whom the test items function just as they do for the non-English learners students, and a second latent class of English learner student for whom the test items function differently. Our analysis will actually be structured to answer three questions. First, are there two types of English learner student? Second, if there are two latent classes of English learner students, who belongs in each class? And finally, what is the role of language proficiency in class membership? That is, are the latent classes tied to the proficiency levels that have been proposed for the test in identifiable ways? The model for mixture item response theory is presented graphically in this slide. The boxes labeled U1 to UP represent test items on the achievement test. Scores on the test items are determined by a single factor, F. The distribution of ability on the factor F is determined by the latent class factor C, which also affects the item factor loadings for one class, but not for others. Membership in the latent classes is determined by students' status as English learners or not English learners, here using the symbol Limited English Proficient or LEP to reflect Limited English Proficient. This variable allows us to place the non-EL students into a known class and the English learner students into the two unknown classes. Importantly, the language proficiency assessments serve as covariates to help determine which English learner students belong in the invariant class and which English learner students belong in the non-invariant class. Although we show only a single model, in truth, we fit multiple models. Model 1 proposes that the test functions the same for English learners and non-English learner students, but the mean and variance of the factor are different. Model 2 posits that the test items function differently for all EL students, but that there is only one class of EL student. And Model 3, which is depicted on the slide, posits that there are two classes of English learner student, one for whom the test functions as it does for non-English learners, and a class of English learner student for whom the test items function differently. So this slide shows the specifications for Model 3 that allows for two latent classes of English learner student. We fit the model to multiple years of data and to multiple grades of data and to both math and English language arts test items. And results were remarkably consistent across the 2 years, the 3 grades, and the 2 content areas. The slide here shows information about model fit, and the next slide shows additional information about model fit. And in the interest of time, I'm not going to belabor these statistics, but I will point out that in every case, the data indicate that there are 2 latent classes of English learner student, one for whom the test items function as they do for non-ELs, and one for whom the test items function differently. And we refer to the former class as the invariant EL class and the latter as the non-invariant EL class. This table shows factor means and variances for the non-EL students and the invariant EL class. It's also possible for us to compare the classes on the actual achievement tests. If we look at the factor means, we see that the invariant EL class tends to perform lower, but that those differences are larger in English language arts than they are in mathematics. And in fact, in grade 4 in 2007, the mathematics factor means are not different. When we actually compare performance on the actual assessments, we see that differences in mathematics are actually small between the invariant class and the non-EL class. And in fact, in some cases, they're non-significant. Whereas in general, the invariant class outperforms the not invariant class in terms of English language arts and in mathematics. The table on this slide shows the effects of the language proficiency scale scores on class membership. These effects are expressed as odds ratios. And so basically what that's reflecting is for a 1 standard deviation difference in the predictor, how much do the odds of membership in the invariant class change from going to the invariant class to the not invariant class. And so, for example, among grade 4 students in 2006, the odds of a student being in the invariant class increased by 57 for each 3-point change in English reading proficiency. Those odds ratios on this slide that are subscripted with a letter A are not statistically significant. And what stands out here in this table is just the substantial odds regardless of year or content area for the impact of reading in terms of changing the odds of going from the non-invariant class to the invariant class. The table on this slide shows effect sizes for comparing the English learner, the EL students in the invariant class to those in the not invariant class on the language proficiency composite scale score, that is ELPSS is the composite score, as well as on the individual scale scores for the language proficiency assessment. For every grade and year, and for both English language arts and mathematics, the groups are most different on reading than on writing, and to a lesser extent on speaking and listening. Generally speaking, the effect sizes for English language arts and mathematics are comparable for any given subtest, both within and between years. An important aspect of any mixture/latent class model is the degree to which individuals can be accurately placed into the latent classes. A measure of placement accuracy is entropy, which has a maximum value of 1, and the average posterior latent class probabilities. These statistics show that the model fit is strong and that individuals are accurately classified into the two groups. And of course, it's reasonable to ask if the latent classes are providing a kind of information that we don't get from the performance level descriptors. And the answer to that question appears to be a resounding yes. If we examine the relationship between latent class membership and the performance levels, we see something very interesting that is quite consistent across grades, years, and content areas. Namely, regardless of the grade, the year, or the content area, students in performance level 1 and 2 have a probability of 0 of being included in the invariant class, and students at performance level 3 have a very small chance of being included in the invariant class. Almost all students in the invariant class are at the transitioning level, that is level 4 of the English language proficiency assessment. However, a significant percentage of students at level 4 are not considered to be in the invariant class. Importantly, the latent classes did not differ on the basis of student gender. However, English learners in the invariant class were more likely to be Asian or white and less likely to be Hispanic. They were also less likely to be on free or reduced lunch in the invariant than students in the not invariant class, and were less likely to have special education placements. Note the demographic variables weren't included in the classification, but groups were compared after the fact. Thus, it appears that the latent classes in this analysis are helping to differentiate among individuals within the highest proficiency category measured on this particular English language proficiency test. Whether we would find something similar on tests in current use is an empirical question. Similarly, we've not considered whether there might be multiple classes within the non-EL population such that the achievement test functions differently for those students. But we have shown that it may be reasonable to question whether the tests are measuring the same constructs in the same way for students who are English learners, and that test developers may need to pay more attention to heterogeneity in language proficiency as it relates to differential item performance. Note, I'm not suggesting that the tests are not measuring English language arts and mathematics for English learners who are in the not invariant class, but they appear not to measure those constructs in the same way. So further investigation of the properties of the tests for these students may be warranted to better support any decisions that might be made on the basis of such tests for individual students. So we have plans to replicate this work with more current assessments, but have not begun that work just yet. We would note that these findings corroborate other work with subgroups of language minority students. Specifically, we've been trying to improve the assessment of vocabulary for English learners through application of explanatory item response models. And in the work that we've done, we compare the functioning of vocabulary items from an experimenter-developed assessment and a standardized test of vocabulary across 4 groups of students, that is, initially fluent English proficient students, reclassified students, students who are current ELs, and students who were never ELs. And on average, words were easiest for the initially fluent English proficient English learners, then for EOs, and then for reclassified students. Words were most difficult on average for English learners. But what's interesting is that when we look at differential item functioning, we don't find differences between the initially fluent English proficient, the reclassified fluent English proficient, and the never EL students. That is, those groups tend to be quite comparable on how the items on the tests function. So what I've attempted to show you today is that groups of students often presumed to be alike are in reality quite different from one another. I would further assert that these differences are meaningful to the students, to their families, and to the students' education. These individual differences are often underappreciated in research, and that needs to change. For English learners, a major source of individual differences is English proficiency, which varies within and between children. We must do a better job of accounting for language proficiency and its effects in comparisons involving English learners if we are to make reasonable inferences about their educational development. We've also looked briefly at context effects and shown that context effects can sometimes conflate student differences across contexts with organizational effects. While it's sometimes possible to unconflate these factors, in some cases the confounds are difficult to unwind. Certainly, more careful consideration of student differences will provide a more informed and nuanced understanding of student and group diversity and contextual effects on student outcomes at the individual and at the group level. Thank you. We need to indicate that this work was supported by various grants, but does not reflect the opinions of IES. And if you have questions, please feel free to email me. Thank you.
Well, first, many thanks to all of you for sticking with us through all the way to the end and willing to join us for some Q&A and chat with David about his great talk. So in terms of questions that you may have, please do go ahead and either post those questions in the chat, which I will be monitoring, or feel free to raise your hand with the raise hand function, and I'll be monitoring both of those things as well. Okay, so for our first question, the question is, David, did you look at whether there were differences in ability to manage the English content area assessments for ELs at levels 1 through 3 of proficiency, depending on the nature of accommodations allowed?
Yeah, it's a really great question. Unfortunately, I don't think we have the data at the individual student level that would let us know what accommodations each individual student had. And it wouldn't have been possible to accommodate that in the mixture modeling in a very easy way. I guess we could have used it potentially as a covariate. But I don't think we actually had that data from the state that showed us the accommodations received by an individual student. But it's a really great question, and something that we potentially could look at if we get an opportunity to do that work again with a more up-to-date data set.
Great. Well, speaking of state level data, one question that I had that I was wondering if you could speak to a little bit is, thinking about sort of what are the trade-offs or pros and cons or limitations of being able to leverage state level data, given, one of the central themes that we heard in your talk was about the role of individual differences. So how can state data help, but also maybe not take us all the way there when we're thinking about trying to achieve that goal?
I mean, I think that's really the major limitation of the state level data sets, or at least the state level longitudinal data sets that I've had a chance to work with, is that they just often don't collect the kind of individual difference measures that we might want to collect to help us know about differences between students. And certainly we could get at certain aspects of students' educational histories, but so, for example, in the state, the data that I was looking at today are not from the state of Texas or from a different state, but in the longitudinal data system that the state of Texas we have the ability to connect up information about teacher credentialing, courses taken. We actually have post-secondary information, college entrance, and a number of different things, workforce-related things that we can bring in. And we have all the different flags that the state collects, but we could look at, say, number of years of ESL services or bilingual services that students got. But that tells us very little about what a student's actual experience is, because two students could be in the same kind of program, but have very different experiences just based on who the teachers were that provided the instruction. And so there are just so many limitations in terms of being able to distinguish the experience of one child from another child based on the kinds of information that are available in those state longitudinal data systems, that I think, being able to augment the state data with data that you collect in the field is what's really advantageous. And one of the nice things about the state data system in the educational research centers in the state of Texas is that we are actually able to take data that we've collected and then merge it with the state longitudinal data system. Now they have to do the merging because it's all done in the background and the keys are kept private. And then we get back a data set that has our data with their data, but we can only look at it inside the ERC. We're not able to bring that data back out. So it limits the kinds of things that we can do, but at least extends our ability to bring in individual difference measures and augment the kinds of data that are collected by the state. But I think often you just can't really get at students' individual experiences based on just on the information that's available in those state systems. You can get at some things, but not at a lot of the things I think that we would want to get.
Great. So the idea of the individual differences and just kind of looking at it from that lens, the way you have been talking about it just now is thinking about sort of the unit is the student. But one of the other things you talked about in your presentation was thinking about other unit levels in the system, whether it's at the classroom level, and then you gave those examples from the district. Toward the end of the talk, you talk about this idea of building a program of research and thinking about sort of these notions of power. When I saw that table that you showed, I was thinking, well, gosh, how many districts would I have to, have in my study to be able to look at that? So I was wondering if you could sort of join those two ideas together.
Sure. So, that one of the things I was going to try to talk about in the talk was when we deal with investigator-initiated studies, the funding is such that you can't do a state level study, right? You're going to be hard pressed to collect deep data on more than say 1,000 to 2,000 students across some reasonable collection of schools. But over a period of years, if you're systematic about the kind of questions that you're asking and you're doing sort of systematic replications of your own work, over years, you can accumulate fairly sizable samples of students, schools, classrooms, districts, and where you might not be able to do that in a single study, but you can do it over a collection of studies, and then those data can be aggregated into a systematic data set. So if you're careful about how you do it and collect similar measures, even if you're not collecting all the same measures all the time, but you have some linking measures and things like that, you can actually expand the power of your own data sets to ask and answer questions in a more nuanced and subtle way than if you just try to do it all within the context of a single study. But it does require that you're systematic and that you develop coding systems and I would say a data warehouse so that you can integrate your data more effectively across projects. And we have been building for at least the last 15 years a data warehouse for our different projects and have accumulated a number of different projects that analyze or collect at least some of the same data. That's allowed us to ask questions of much larger samples, both in terms of students, classrooms, teachers, schools, and districts than we would have been able to if every study was just something in and of itself and only operated in its own universe.
Great. I'm thinking about folks who are either beginning a program research or who are early career. Do you have any sort of guidance or thoughts for them in terms of thinking about these issues a priori?
Yeah, I really encourage you to work with and hire professional data managers because they will help you. I mean, part of what helped me was that throughout school, I was really interested in data management and data analysis. So I started thinking about the ways of building data systems that would allow for integration across projects. And as we would design new projects that were sort of building off of the old projects, I needed everything to be able to line up so that I could aggregate the data. And you can't do it all yourself, but if you hire professional data managers, it can help quite a bit. But I think the first order of business is just to have that sort of long range view that I'm doing lots of studies that are focused on this particular problem. If I'm going to collect similar data, I collect it in the same way using similar instruments. If I code it in precisely the same way, I can aggregate the data more effectively. So it's starting out with that idea in advance. And we started early on coding everything at the item level and creating our data sets at the item level so that we had the ability to develop our own scales and create our own linking scales over studies because we had captured everything at the item level. And so starting out with that in mind, as opposed to deciding after the fact, it's too burdensome to go back and enter the item level data often, or you even discarded the form, so you can't even get at the item level data. And so if you start out with that perspective in mind, I think how you design your data systems can be better prepared to allow you to integrate that information over time. And it's actually paid dividends for us in a number of projects. And we had a scale-up project that was built off of some intervention projects that we had done focused on English learners. And the scale-up project came about 8 to 10 years after the original individual intervention studies that we had done. And when we were applying the same sort of screening criteria for recruiting students, identifying who the students were, the sort of the members of the target population, we found that students were performing better on the screening test. And so now we were using a different test, but it was supposedly the same test, right? It was a different version of the Woodcock language proficiency test. So, and it was sort of anomalous in that they looked better on most categories, but in one category, they actually looked worse. Well, what we did was we took our older data and the new data, and we created a common scale across the studies. And we found that, in fact, the students in the new studies, that is the number and percentage of students who were meeting the original screening criteria was actually much lower, that the students who met the criteria were actually performing at a much higher level. And we wouldn't have been able to do that had we not actually coded everything at the item level so that we could integrate our old data sets with the new data sets and distinguish that was in fact what was happening. And this makes sense because over that 10-year period, there had been a tremendous increase in focus on English learners and on early reading instruction for English learners. And so it made sense. And we were for part of the study, we were in the same schools and same districts that we had been in 8 to 10 years before. But the performance in those schools had changed quite a bit over that period of time. We wouldn't have been able to completely understand that if we didn't have the ability to link our instruments across time like that. So.
Thanks for that. So I'm going to read the question that Liz just posted in the chat. Do you have any recommendations for do you have any recommendations for the community in terms of defining shared metadata and data fields that should be collected and could potentially facilitate cross-investigator research? And there is a second vote for the importance of that question.
Yeah, it's a really good question. And I have to say, Liz, I don't think I have strong, I can tell you we've tried to do this across some networks, and it can work. For example, we've actually been doing some work on reading development, where we've integrated data from our studies in the Reading for Understanding network with the studies from Florida State, Chris Lonigan's group, as well as Laura Justice's group at Ohio State. but that was partly facilitated because we were all in the same room having conversations. And so we were using similar instruments, and I was aware of those data collections. And so we were able to get together and sort of combine data across time to be able to do that. It's possible when you have networks of people that are working in related areas, but I don't have a general recommendation for the field as a whole. I mean, obviously, achievement data, if you're focused on English learners, trying to get at language proficiency assessment, most people are going to be limited in how much data they'll collect with respect to language proficiency. There are some suggestions about specific measures that if you can only collect one or two, what should you collect? And I have some, I have some thoughts about that, but it's probably a little too much in the weeds for this conversation. But I think the way to do that is really to establish networks of people that are working on similar problems and come up with a plan. And in part, that like the NIH toolbox is a useful thing, but it's also a limiting thing in the sense that in an effort to find measures that everybody could agree to use, it ends up being a relatively narrow construction of certain constructs and not necessarily always helpful. So I think forming networks is the way to get started on that.
Great. I'm going to refer to a new question in the chat that follows on Liz's question. I want to make sure I get the question right. So it's asking about how people should be thinking about having unique IDs that can be consistently linked to the sources of data. So if I botch that question, please do.
I think I understand the question. So we use, I assume Anjali's talking about the IDs for the students, and we have, you need to understand the ID system that your state is using. And so what we will attempt to do is to get the PIEMS number, which is the student identifier number from the state of Texas. We try to get those identifiers from the schools. Then we build our own project IDs that are completely different from those. But the PIEMS number, the student name, and the student date of birth are the key ingredients for linking in Texas. And if I wanted to link my data over time, that PIEMS number is actually a number that stays with the student as long as they're still in the state of Texas. If I then wanted to link that data with data from the state of Texas, they would take that PIEMS number along with the date of birth and the student name, and then they would link it with the ERC data, and I would get it back as an integrated data set, but with all that information stripped out so that I can't identify the student any longer. But I can at least have them integrate the data that we've collected with their data. We always keep those personal identifiers separate, and the people that can actually access those are not necessarily people that can get in and analyze the data. So the nice thing about the warehouse that we've built is that individual projects can be restricted to only people that are authorized to see the data from that project, even though the data in the warehouse are completely de-identified. All the identification apparatus is sort of in the back end of the warehouse. People can't actually get at the personal identifying information. All they can get at is the de-identified information.
Great. I'm going to read a great question that Fiona posted in the chat, and then after that, Emily's hand is raised, and we'll do a quick time check after that. So Fiona's question is, if you are reusing data in later studies, do you have to go back to districts and update data sharing, data use agreements, IRBs, et cetera, or are you able to negotiate permission for unknown future uses, or is this all publicly available data?
That is very dependent on the district that you're dealing with. Most of the data that we collect is data that we, where it's it's our measures and things like that. And so we have permission to use those data, in the future, but we do have to go back and get IRB approval for future studies. And usually we're working with de-identified data, and so the use restrictions are limited there. The restrictions on the use of the data are not too great, but we do have to submit an IRB application for it. And we do that when we have to integrate data and those things, but we don't have to necessarily get another use agreement from the district unless the district signed a restrictive use agreement initially. So for example, some districts that we work in want us to destroy the data after the project is over. We try very hard to get them to not impose those restrictions, and certainly on the data that are de-identified, because it limits the utility of the data that you've spent a lot of time, effort, and money collecting, and they could be useful for other purposes other than the originally intended purpose. But it just depends on the district. So I'm thinking of particular districts in Texas that are more restrictive than others.
All right. Emily, we'll take your question now.
So this conversation is making me think about a tool that we have at IES, which is that there's this public access requirement, and some of you are required to create data management plans and plan to share final data sets. So I know, and it occurs to me that, in my role, I'm a program officer. I'm responsible for working with many grantees in a specific domain. My domain is social behavioral. Like, what are your thoughts, David, about what somebody like me can do to sort of encourage people to be thinking long-term? So you're right, we can work in teams and we collaborate with certain people, but program officers have a unique bird's eye view of a larger group, and we can be influential. I mean, we work with applicants, we can encourage people to use certain measures. We cannot require things, but what are your immediate thoughts about that as a tool for us to facilitate this kind of idea?
Well, I mean, I think within any given area, if there are some gold standard measures for different things, advocating for people to make use of those gold standard measures is really advantageous, both across projects done by the same investigator, as well as across projects done by different investigators. But going beyond that, it's really encouraging people, cajoling them into understanding the importance of collecting item level information and encoding, that is, storing item level information. Now, that may seem like a trivial problem, but in fact, you need to not just store the data at the item level, but you need to store the items. That is, you need to know that this item was worded in this way, because when you go to the future, knowing that it was, social behavior scale 1, item 1, if that item changed from one point in time to the next, you don't want to keep calling it the same thing. So understanding that you have to build a database of the data, not just the responses to the data, but you really need to have data about the data that's being collected. I think that facilitates building these kinds of archives and making them useful across projects. Because let's say that you measure this, you decide to measure student motivation, and you have a sort of a measure that you're using that's an amalgamation of other measures. And if you've stored that at the item level and you have data on the items that are actually encoded, when you go to do a future study, if you don't use that same questionnaire, but you at least use some of the items from that questionnaire, you can at least link the old questionnaire to the new one. So you have the ability to do other things if you've captured that information. But if you haven't, it can be daunting to go back and try to do that after the fact. So getting in the habit of building your data so that it's future-proofed is really, I think, a key for junior investigators to understand. And it's true no matter what field you're in, whether you're a psychologist doing neuroimaging studies, or an educator doing behavioral interventions, or doing the kinds of sort of cognitive behavioral studies that we tend to do.
Thank you for that, David. I really love sort of the future forecast perspective on the question. So I am noticing the time, and I think we are out of time for questions, because we do want to allow a few minutes for Drs. Albro and Laughlin to say some final words. So before we end the Q&A, I do want to just again thank David for his talk, and thank you all for the questions that you have submitted. Again, it's been my pleasure to co-chair the meeting, and I hope you all had a productive 3 days, and looking forward to seeing you all soon. So on to our commissioners.
Thanks, Dory. And I also want to thank everybody for attending the final session. Thank you.
I'm going to start. Hi, everybody. Liz and I have talked about the things we want to say, and we each feel as passionate about it, but we divided it into two. And the first thing we want to say is thank you to David, because when we asked David to give this talk, he was in the middle of preparing his talk for SRI. And so to keep, to have two very thoughtful talks in this short period of time really says a lot to the amount of work that he's been putting into it, and we really appreciate it. And you have great fans in IES. Thank you. And thanks, because it really added to the conversations that we've been having over the 3 days, and leaves us much to consider as we go forward, thinking about it at IES, but also individual researchers thinking about their work. And I want to thank everyone. And I know at this point we're starting to need to take care of the rest of our lives, but I want to thank everyone for bringing their A game to this meeting. The sessions were terrific, with thoughtful presentations and discussion, and it really exceeded our thinking about what might be possible in a virtual format. Hopefully we'll continue these discussions and throughout the year, and bringing them into the work that we do. One of the great things about having a virtual meeting is that we can go back and listen to things that we liked, or to listen to things that we didn't get a chance to see because they competed with other things. So remember that tomorrow or next week, or whenever it's convenient to you, you can download the sessions on the meeting platform, which you can find at the landing pages for both NCER and NICSR, and listen to these at your leisure. And then I'm going to turn it over. Oh, I have one more thing. Please fill out the survey. Believe it or not, within like a week, I think we have a meeting to start planning next year's meeting. So we really use your feedback. We appreciate your feedback. I'm particularly interested in knowing whether or not another virtual meeting is what people would prefer, or you'd prefer to, once again, be in person, fingers crossed that that's appropriate. But please fill it out and let us know. Now I'm going to turn it over to Liz, and thank you all. I really appreciate it.
I know. Well, Joan wanted to go first, so she got to say the big thank you. So I'm going to also say thank you. I really enjoyed the sessions. I feel like I've learned a tremendous amount, and honestly, that's the best takeaway from a meeting. It's been great to see everyone. It's not quite as much fun as passing in the halls, but it's good. But in addition to thanking David and to thanking all of you, Joan and I want to extend once again our heartfelt thanks to the co-chairs, to Dory Laforette, who's here, and Brian Boyd, for all the work that they've done. We want to thank the members of our team who have taken the lead in standing this up. Christina Chin is the master behind all of this. She coordinates us all. She tells Joan and I when we're behind and when we need to respond to things. Katie Taylor and Akila Nelson from Joan's team, and Helen Kim from the NCER team have all worked together. And so if you know them, if they're your program officers, give them a shout out, say thank you, because this is in addition to their day job, and they've done a fabulous job as far as we're concerned. We want to thank also Bizel and the team at Clarity, the tech folks who have made this meeting run incredibly smoothly. I have to say, I didn't have any glitches, which is unbelievable to me, given how many I still see, even though we've been living in this world for so long. And so just to close us out, so please, everyone, stay healthy, keep doing good research. And please, Joan and I would love to hear from you if you have other ideas, feedback, thoughts that are beyond the survey, reactions to sessions. We are here, we are listening, and we are keeping our fingers crossed that next year we can see each other again, whether it's in person or virtual. So I think with that, I'm going to say thank you, unless Joan, there's something I forgot to say.
Oh, great. Thank you.
Okay. All right. So thanks again, and have a great afternoon. And
All right. Take care.
take care all.
Bye.
Bye now.